Our mentors, as Jessica mentioned, is Diego Parra, who is the DO in Linked AI, Paula Villamarin, and also Christian Garcia, as Jessica explained some minutes ago. The goal of this project is to build one anomaly detector, uh, but using synthetic data. In the next slide, we will going to explain what means synthetic data. And just in order to put some numbers, because one objective without metrics is not one objective, we determine that to have more than 70% in accuracy in this anomaly detector will be a good target in order to determine if we had success or not. Next, please. So I'm going to talk about what is anomaly detection, what we use one denoising autoencoder. And in this slide, you will see that we have some original image. Let's see that we are in one production line in one factory, and in the next slide we'll show some cylinders. But in our case, we have some walls. In this case, we have one original image, and we include noise to this original image. Why? Because we need to train what the neural network with one architecture like the autoencoder, in order that this deep neural network be able to erase the noise. Yes, the objective of this autoencoder is to erase the noise, like I am putting in the second image. So as output of this autoencoder, our our goal for this part of the autoencoder is to have one reconstructed image similar to the original image. And as you can see, we have here one what feedback here in order to determine the error. This error is one comparison between these two images, the original and the reconstructed image. And based on this error, we are going to train the autoencoder with deep neural network. And as you will see in the next slide, we are using some convolutional architecture. Thanks, Jimena. What happened with when we have the trained deep neural network autoencoder? When we have this deep neural autoencoder, we can put any image from the, because we need to determine if this picture have one anomaly in comparison with with one normal image. So let's to remind that we have in this case the trained autoencoder, and when we put one original image with anomaly, what happened? As we have trained the deep neural network, we expect that the autoencoder be able to erase the anomaly. Yes. So in case to have one anomaly, our autoencoder going to delete it, to erase it. And when we compare both image, yes, I'm going to determine if the original image have anomaly or not. Yes. So that means that we have two steps. The last one was to train the deep neural network with some convolutional architecture. And in this second part, we use the trained autoencoder in order to determine if we have one anomaly or not. Next, please. Which are the challenges in this case? The first one is that we are not using noise like some examples that we can find in the literature or in some papers. They use some random noise. but we are using synthetic data. Our peer Jimena going to explain what means synthetic data. And the second one is that we are going to use some denoising autoencoder. Why? Because in one line, in one production line, we are not able to ensure that all the pictures have the same angle, the same brightness, the same environmental condition. So it's not easy to have the same picture. Probably the size is different. I mean, it's the same component from the factory. Let's say the cylinders that we're going to look, but we can have some changes in the angle of the camera, or probably in the brightness in the environment. So it's necessary to capture the intrinsic features of the objects. Yes, because we cannot do one comparison pixel by pixel just in order to say, we have one anomaly or not. No, we need is to capture the intrinsic feature of the objects in order to avoid this kind of variables. And at the end, to recognize the anomalies. Sorry, and the other challenge is that as the anomalies, I mean, the anomalies is one strange event. Yes, so that means that this is not possible to have, I don't know, 1,000 or 10,000 or anomalies, because it's one strange event. So that means that our data is unbalanced, because we can have a lot of pictures without anomalies and only 3 or 10 with anomalies. So it's necessary also to have this into account in order to have one nice architecture. Next, please. This is our big blocks, big block diagram. We have one part that the name is pre-processing. It's necessary to collect the data, to organize it, to define what kind of noise, as I mentioned, is synthetic data, and to upload this to our data repository. Second one is related with the machine learning model. Yes, the architecture, to define the architecture, to define the number of layers, and Heimer is going to explain this part. And the last one is based on the training model. Is necessary to determine some threshold based on one histogram. It's necessary to explain it, and Heimer is going to explain it, and Maya. And after it, to compare the image, the reconstructed image, and to classify it in anomalies or no anomalies. We also include in this presentation the names, of some libraries, like Flip, that this is really important in the synthetic data creation. Other ones were recognized in machine learning area, like NumPy, OpenCV, Seaborn, Scikit. And also we use White and Bias, that this is one library that this is able to do some kind of tracking for the different experiments that we did in this project. Next, please.
Okay.
Thanks, Jimena. You can continue.
Thank you, Adele. Um, we all the data that we used to train in our model was synthetic data created with Flip library, and we took some image without anomalies and add noise. We have two types of noise. One is like to real anomalies, and the other is random objects. For example, animals, plants, and other objects. We use two datasets from COL. This is the first crack dataset. You can see some examples, the original image with and without anomalies. And also can see some examples about the synthetic data that we use to train in our model. Okay. The second data set was cylinder. This represents a real production line. And also you can see some examples about the original image with and without anomalies and synthetic data. We did different experiments, and all we have a data set with 10,000 synthetic image. The parameters that we modify in the experiment was two. The first is the relation between original image and how many new synthetic image. We have 4 combination, 1 to 1, 1 to 5, 1 to 10, and 1 to 50. The second parameter is about the noise. We create different data set, some all with only noise, similarly to the real real anomalies, and all and other with only noise with random objects, and emits 50 to 50%.
Hello, guys. Great. Well, can you hear me? Yes.
Yes.
Okay. Let me come back here to one part of the presentation because I don't know why it's ended. Okay. Well, now you have a general idea about the data, no? You have a general idea about the model, and you have a general idea about synthetic data. Now it's time to understand the model a little bit deeper. The best way, no, it's not the best way, it's the most common way to solve this kind of problem is with supervised learning. But because of the nature of this problem, where, as Abdel told us, most of the time we have an unbalanced data set. In real life, we have unbalanced data sets. So we have many pictures or images from clean images without noise, and just few images with anomalies. That's the real life. For that reason, our approach was different, and we started to work with unsupervised learning, specifically with autoencoders. And there are many autoencoders, no? The most common autoencoder is, for example, that you can see here on the top of the image, where you have a bottleneck in the middle, and you can see that in that part in the middle, we have fewer dimensions than the input. Every line, if you understand more or less machine learning, you know that every line means every layer in this model. And as I told you, the middle has is smaller, so has fewer dimensions than the input. That's the common way. If you read papers, if you read everything about autoencoders, this is the common autoencoder. But we decided to use a different kind of autoencoder. This is called overcomplete autoencoder. And you can see at the bottom of the image, where is the opposite. The middle, the latent space, has more dimensions than the input. If someone that have a notion about this could say, okay, this model has a problem. That model is gonna learn the identity. Well, that's not true for this approach. Why? Because as Abdel told you before, the input always will be a synthetic data, always will be an image with noise. And the output, at the expected output, will be always a reconstructed image. No, always would be an image without the noise. For that reason, we decided to use this architecture. Another trick, another thing that we added to this architecture was the concept of dilated convolution. We didn't use the common convolution that we can see in every paper. We decided to use dilated convolution because with this kind of convolution, we can keep the resolution of the image without losing information, and we only started to add filters in order to get more dimension and learn more about the input. Okay, in this image, I think that's sum up everything about the project. The input is a clean image, the original image, right? We pass the image through the flip library in order to create synthetic data. So after that, we have image with noise. We take that image with noise and we are passing that image through our model. This is our final model that you can see here. It's not too deep. To be honest, it's small, but was enough, was very good solving this kind of problem. You can see here the number of filters. Our input was in the range of 227 by 227 pixels. So this is a small image. And we, at the end of the autoencoder, we got the reconstructed image. Okay, something is very important in this approach, and is the loss function. We tested many, hundreds, thousands, millions of loss functions. Well, most of the papers always say that the best loss functions is the L2, L1, the mean score error. No? The mean score error is the best way to compare input with outputs with images. But in this case, it's not true because the mean square error compares pixel by pixel. And for example, as you can see here, the original image against reconstructed image, if you compare pixel by pixel, you can see that there are many problems here. If you compare pixel by pixel, it's better if you start to compare the structure, no? Everything together. So for that reason, we use the structural similarity index measure that not only takes into account the pixel by pixel difference, it also takes into account the relation between pixels and the structure of the image. For that reason, this loss function, that is a custom function, we made it, works very well for us. Okay, what happens when we have the difference with SSIM between the input and the output? Well, we can create an histogram. And that was our reaction when we finally got a cool histogram, because it was really difficult at the beginning. But what is the histogram? Okay. This is a histogram that we created for one of those data sets. As you can see here, we have two groups, two data sets, the blue one and the orange one. The blue one is data without anomalies. And the orange is data created with synthetic data. No? It's noisy, it's data with anomalies. If we graph that information, the difference with the SSIM loss function, not the SSIM difference in this case, we graph that in the histogram, you can see that there is a point. There is a specific number or maybe a region where on the right, you can see most of the images that are part of the set of anomalies. And on the left, the set without anomalies. You can see it better in the magnifying glass here that I'm showing in that part. Okay. You can see that in this case, we've chosen .004, for example, right? That's the point. But could be 005 or could be .006 because it's like a region, no? We decided to take 004. Why? Because the smaller the threshold is, the metric, the recall metric is better. I'm going to explain a little bit better why recall is the most important metric in this kind of problem. But thinking that It's because that metric is very important that we decided to always the smallest number in the region in the histogram. Okay? Everything that we've done before was with synthetic data. Remember that, was with synthetic data. We train the system with synthetic data. We create an histogram with synthetic data, and we define a threshold to define if it's anomaly or it's not anomaly with synthetic data. Now, let's see what's happened when we pass real anomalies through the model. And this is the result. The first row is the input of the autoencoder, and the second row is the output. As you can notice, it works really well. You can see that it's able to detect the anomalies and shows the, in this case, shows the anomaly in green. This is for the cracks dataset. Let's see what happens with another dataset, with the casting dataset, this kind of cylinders or something like that. This was much harder to tune in. It was quite difficult, but finally it works. Check it. For example, the column number 4, right? The image 564. You can see that this image has an anomaly that is a small dot on the right. But the system was able to detect that kind of anomaly, so it was great. So finally, the model is working pretty well. Okay, remember that Jimena told us that we created different kinds of data sets, no? So let's see what happens. What is the response of the model depending on the training data sets? Okay, I'm gonna show you something that is our experiments. This is the platform called weights and biases. It's really cool. And you can track here the experiments, everything, your machine learning model is cool. Here you can see 12 experiments. Okay. Every experiment was divided in the same way that was divided the data set that Jimena told us before. For example, the experiment number 1, you can see here, from one original, one synthetic. That means that we take one image without anomalies. We created a synthetic image, adding noise or adding something to that image using Flip library. And the next part that say 100% random objects, 0% similar anomaly means that we use 100% different kind of objects, not only objects that are similar to real anomalies. Let's see it because it's easier when we see that kind of things. So this is the first experiment. For example, here is the data that we use in that model. We use random objects as synthetic data, as anomalies. You can see here a monkey, a book, a whale, bueno, many things that we use here. Also, you can see beside it the clean image, no? The output of the model. Let's see another experiment. Let's see, for example, another one with another kind of data, no? Of synthetic data. For example, the 11 experiment. In this experiment, we use something different. This is the synthetic data use. Okay, you can notice that the image is similar, no, to a real anomaly, but was synthetic, no, it's not real, but it's closer to the real anomaly. Now, let's see what's the difference for the model, no? That's the part that is interesting. Okay, here we have different metrics. Let's check the recall, but the recall for real images. Let's see what happens with real images when the model was trained with synthetic data, but different kind of synthetic data. Here is the graph. Okay, you can notice that, no? You can notice that the difference pretty small. It's really, really small. Remember, for example, the experiment 1, because it's the first one at the top, is almost the same that experiment 11, that is this one, that the green one, and use different kind of synthetic data to train the model. And the answer was almost the same. So it's pretty good. So for this kind of data set, cool. We can use every kind of data set and everything works. Okay, let's see what happens with the cylinders, with the casting data set. Okay, here the same thing, the same division with the data sets. Okay, let's see. Example, experiment 1 again. In this experiment, this is the data used, for example. In this case, for example, we use anomalies that are similar to anomalies. Similar, no? It's not real, no? You can see the anomaly go, for example, in the background. That is not real, no? Because the anomaly is only in the cylinder. But it is one of the data sets. Another one could be, for example, let's see, another one with a different data set. For example, this one, experiment 2. Experiment 2. Oh, the graph, where is the graph? Where is the graph? Oh, data graph. Ah, here. Okay, again, we use random objects, no? Random objects as anomalies. You can see here, for example, an elephant. We can see here a bird, orange, a ball. Okay, let's check. Let's compare the models. Let me organize this a little bit better. Maybe organize it with the recall. That is the most important metric. So recall. Okay, that's fine. Recall for real, recall for real. Okay, recall for real dataset. Okay, different, no? Really, so different. If you compare this result with the result that we get with the cracks dataset. Here, for example, the first one, no? On the top, experiment 2, pretty bad, really bad. In this case, we use random objects as synthetic data. In the middle, the experiment 3 and experiment 1, 2, we use 50-50. 50% synthetic data with random objects, 50% with synthetic data with similar anomalies. And at the bottom, you can see experiments that use anomalies that are really close to real anomalies. So in this case, it's different from the previous case. And in this case, it's very, very important the kind of synthetic data that you use. So as you can notice, it's not always the same result. This is our final numbers. Okay, at the end, for the cracks data set, we got up a perfect model, to be honest, almost perfect. And for casting data set, we got very cool numbers, and the recall was around 85%. I'm really happy with this result. It's awesome, this result, because I need to say it again. This was trained with synthetic data. This model had never seen before a real image and was able to detect a real anomaly. So the numbers are pretty good, pretty good. Okay, let's continue with Maya.
Thank you. I'll take the screen.
Give me a second.
Can everyone see the screen?
Yep.
Great. Anomaly detection. This is where we're going to actually show you the running of the anomaly detector. First, you have to train your model. Training your model. Now this is the architecture. Heimer talked about the dilation. You can actually see here where it goes from 3 to 32 to 64 to 128 to 64 to 32 to 3. That's the dilation. That's the difference. That's where the architecture expands rather than contracting. Here we look at the loss. Now, the goal with the loss is that the loss decreases and the accuracy increases. It takes a couple of times, to say the least, for the accuracy to increase the way you want it to. But as you watch these numbers, you see it increase. We use the SSIM loss, as mentioned by Heimer. Here is where we actually put it in to calculate our loss. It worked the best. Next, we have our histogram. Our histogram is gold. This is where you find out what you need to do, what you can do, and how it changes. I'll move this here so you can actually see when Heimer's actually showing you what the differences that occur in the histogram. Without the histogram, you're kind of going blind. These are the data sets. We input images at random. You have the original image, and then you have it with an anomaly. The output images, you hope, coincide where it says there's no anomalies with that original image, and there's anomalies detected with the next. Here we're taking you into another one. Here we have, again, an original image, but now we have our noisy images. Again, we're working with synthetic images. We're going to have another histogram. For each time you go through it, you want a histogram. You need to know where you're going, what changes you need to make. We use the hash library. Abdel found the hash library very useful in helping with the histogram. Now we have our histogram of what we just ran. We can see the variations, the differences, the changes we may need to make. This is the gold of it. Now we're going to get into something called weights and bias, something that we definitely need when doing machine learning. It automates all this information. Here you have your histogram of the actual original data, and you have a synthetic. For each data set you input, you get histograms on each thing. Weights and bias, we'll talk about it more later. You saw Heimer reference the log chart. With a simple bit of code, you can get a log chart on each thing. You can get your loss, you can get your MSE, you can get your F1 score. Not only will it put in a log chart for you, but it'll make it a nice, pretty chart, graph. Heimer was showing the graphs with the F1 score for the real data set. Here you see the bars and how it coincides. Do you need to change something? Do you need to add something? Do you need to find another data set? Here's your GPU. Something you might not think about. How expensive is this model? Do you need to worry about that? Is there a budget for your expense with this model? This will tell you right here. You can see the power usage, time spent accessing memory. Thank you for that. I'm going to exit the screen. And if you bring up the slides. Next, I'm going to talk about challenges. Challenges. One challenge was the image similarity matrix. The quantitative evaluation of similarity between two images. The less complex models help you solve this. You need to calculate how similar the images are you're working with. Another reason that you use the histogram. You need to determine the similarities so you can determine the outliers or anomalies. You need to find a proper data set. You must have a data strategy. Familiarity with the subject of the image. You may need an expert to determine what is an anomaly. If you don't know what you're looking at, like our first data set, we had some pictures from an auto company. Well, we couldn't clearly recognize what was an anomaly and what was not. So we needed an expert. That's something you may require to help you choose your data set. You need a clear image of the original data set. Original needs to be to represent the variations of the environment that this anomaly needs to be detected in. You want to avoid overfitting. You ask yourself, how much data is needed? What data is not available that you may need? Searching for balanced data. Heimer mentioned we had unbalanced data. There need to be changes made in the model or changes made in what you're using to create the model. The balanced data determines if the number of positive values and number of negative values are approximately the same. Having a balanced data set, you can generate higher accuracy in your model, higher balance accuracy, higher balance rate detection. When you're talking about that, we had the experiments. As Amanda was talking about the experiments, we had 1 to 1, 1 to 5, 1 to 10, and 1 to 50. That was to see our balanced data set. Another thing we had to learn how to do is collaborate with a company. There's a thing called an NDA. It's a non-disclosure agreement. It protects the interests of your client and the interests of the company you're working with. The client needs to have their interests protected, and the company you're working with might not want information shared. Time schedules. Coordinating a meeting can be challenging. When you're just on a school schedule, you might forget all the other things that come into creating a meeting. Time zone. I was in the United States in Connecticut. My peers were in Colombia. For half a year, we have an hour difference. We also had some collaborations that we needed to do. So I had to explain to them that my hours will change because of daylight savings, and we'd be the same time. Next slide, please. Future improvements. At this time, we need a human expertise to choose the proper threshold to follow based on the real data or synthetic data. This can be improved by automating threshold selection. Let me explain. Sometimes the human expert knows exactly what threshold they're working with, and you can make adjustments to create that threshold, and they can choose to go with the results from the synthetic data or the real data, and that's up to them. If we automate this, this might make the process go faster. Next slide, please. What did we learn? We learned about the life cycle of machine learning. It's a little different than I learned through the projects. You acquire and explore your data. You have to have a data plan. You model the data. You interpret and communicate your findings. This is important. When you're sitting there with the data coming out, you want to talk to your peers, you want to talk to your mentors, you want to see what these results mean, how they can be improved, if this is the right direction you're going in. Implement and deployment. Let's implement and document. Document, document, document. We documented it with a blog. We also took notes in our meetings to see what were our next objectives. Now, this life cycle is not linear. It's cyclical, and it can go back and forth. You might have to go in between acquiring the data and modeling the data as the model needs. Synthetic data, open source contributions. The FLIP library, I talked about automation before. Using the FLIP library allows you to create levels of synthetic data you can't create with Photoshop. If you're not familiar with Photoshop, you take the image and you try and transplant the image on something else. No, use FLIP. Use the FLIP library. It's a Python library. Most of what we're working in is in Python. It's LinkedAI's FLIP library. New architecture and method for autoencoders. Most autoencoders, as Heimer mentioned, use dimensionality reduction. Christian suggested to use dilation, and it keeps the resolution of the image. And in this particular thing, trying to detect an anomaly on an image, you really want to keep the integrity of the image so that it's not detected as an anomaly. Instead of the middle layer of the autoencoder having the smallest dimensions, as Heimer mentioned, we dilated it. Weights and bias. Weights and bias is amazing. It's 3 lines of code. You load the library, it's a Python library, you load it, and then you put another line of code where you want it to log the information that's coming out of your model. It automates the histogram for you, as I showed. It does the math for you, and for machine learning engineers, it allows you to focus on training the model, creating the data sets, improving the accuracy and decreasing the loss. Use of a histogram as one way to determine threshold. Your histogram is your eyes and ears of your model. You don't know if you're making changes. It's also the eyes and ears of your data. Is this data working? Is this data something you can use? Do you need to check your data again? Do you need to create new data? It determines similarities. It helps you find where the anomalies are from the threshold. Another thing we came into that's not listed is communication. We're speaking in 2 different languages, and my peers were very, very accommodating with English. My Spanish is not as good as the Spanish of my peers, and I appreciate that. Thank you very much. Abdel.
Abdel, just in case you're muted. All right then, Jaime, you're muted, sorry. There you
Okay.
go.
Well, okay, there are many things to do now after this. Many things. Okay, we can improve the model. For example, the threshold now is only with the histogram, and visually see what is the best threshold for the model, for this case. Depend of the case, no, as I told you before. Also, we can improve it, for example, working with video is another thing that we can do in the next steps. Could be awesome. But the model, as you notice, I'm going to show you maybe at the end of this presentation how it works, and you can see that it's pretty fast. So it's easy to pass this model to a video problem, not the image problem. Next one, please. Ethical implication. Well, there are many ethical implications, but for us, for me, I think the most important one is, for example, if you are in a product line, for example, and you are taking pictures, images from the product, and the product is something for the healthcare system. So it's important that the product always is a perfect product. No, if something is bad, probably you are putting in risk the health of people. So that's an ethical implication. So for that reason, we decided to use the recall as the most important metric, because the recall is a metric that takes into account the false negatives. The false negative is that kind of problem, no? The one it determines that something that doesn't have problems in reality has problems. Next one. Conclusion. Well, there are many here, and some of them, in a nutshell, is that the unsupervised learning way to solve this problem is very useful because we have always unbalanced information, but also sometimes we don't have enough information with clean images. So for that reason, the flip library and synthetic data is key. It's very important here also, because in that way we could put in balance that kind of data, and we're able to solve the problem in a better way. Right? Also, we learn a lot of things. We learn about synthetic data, autoencoders, something like that. But I think in a nutshell, that's the most important thing. And thank you. This is a general approach about this project. And now Jimena is going to show you a little bit how it works.
Okay, in this mini application, we can select the dataset to work. For example, we can select cracks or cylinders. In this case, I select cylinders and upload an image. One moment. For example, in this image has anomalies. We can visualize the original image and analyze. The output in this case is image and have the anomalies in green color. For example, if I select other image, for example, this, and we can analyze again, and again see the anomalies. Now I select image without anomalies. Analyze. And in this case, this label says that not anomaly detect. Other example, in this case with cracked dataset. Okay. For example, this, and analyze, and we can see the anomalies. Thank you.
Okay, thank you guys. Thank you for listening to us. And if you have any question, just tell us.
All right, then I think, Gabby, slept through your whole presentation, so it means that it was very interesting for everyone that is attending here. Not for babies, though. All right, guys, I am so proud. So here in the chat, you can see Rolando saying, congratulations, that's an amazing project. You guys rock. Are you going to share or publish your work? Will it be a paper, a notebook, or another project resource available? That's an interesting question. Do you guys think you're gonna publish that as a paper?
I'm not sure if it's a paper, no, but now we have a blog. We have a blog. You can check our linked profiles. We can see that we have a blog. It's detailed, it's very good, I think. And also there is a link to the GitHub, so you can see it there.
All right. Then we have also here Felipe Cerny is asking, what industry can be improved with this project?
Okay, the focus was manufacturing, no? The focus was a line production, production line. But we can use it in different contexts, to be honest, no? Depends on your imagination, depends on what kind of things you want to do, sorry. So yes, as you can see, it's general, but you have to do a fine tuning in order to use it in a different context. But in general, you can use it wherever you want.
Nice.
Okay.
Maya, what do you think?
I'm gonna share you on this.
What do I think about what can be used for future implication?
Yes.
A lot of the future implications, as Heimer said, it depends on your imagination. It also depends on how detailed the information you want. You might have to, again, with a human expert, you'd be able to determine how finely tuned you want the anomaly detection to be, as opposed to not finely tuned. You can calibrate it for a large scale, sort of an aerial photo of maybe looking for buildings that may have fallen or not fallen in an earthquake, or you can get it even smaller for a smaller scale where you're just looking for cogs connections in your assembly line.
Yeah, that is actually pretty interesting to take like that after an earthquake, like the one in Haiti, for example, you can take an aerial picture with a like the satellite that Google Maps we uses, and then identify buildings comparing pictures. That is actually pretty great. All right, so guys, Heimer just put on the chat the blog post that they had. So Fernay is asking, do you think it's easy to implement in an industrial in terms of time responses, for example, in flowers industry?
Well, I don't know anything about flower industry, to be honest, but if you can take pictures with a certain range of difference, I mean, because always it's important to have a set of images with different approach, but if differ too much, it's a problem. No, you have to keep always try to take pictures with the same light or angles and things like that in order to get a better response from the model. So I'm not sure in the flower industry that is possible, because I think always is in the countryside. No, the weather is different every day, so the picture is different every day. So I don't know. I don't know. I need to take that kind of thing into account.
Yeah, that will be like a case of study, because in a way, these type of models are good for industry that have to have the exact same product every time. So let's say an iPhone, I don't know, the AirPods, a modern box. Like once you have like the same product every day and in every aspect, it needs to be perfect, then the anomaly detection will be easier to identify. Something that it's natural, that it's not a cookie cutter, like a flower, because flowers, yes, they have the shape, but some flowers have different shapes, and it doesn't mean that they're wrong. It just means that they are like, it's nature built, it's different. So in that case, I will think that it will be harder in a way to identify anomalies, because maybe what you can identify as an anomaly, I find it like normal in a flower. So yeah, I think that's an interesting question, but it's also like something that it will have to be tested in order to be put in production. So I don't know, maybe the ones that are here that are next going to take machine learning or are going to build a final project, if you're interested in the flower sector in Colombia, then maybe you can do a model to identify anomalies in flowers. All right, so you guys, I don't know if you guys have, the attendees have more questions. Anyway, I'm gonna take this time to congratulate Maya, Jaime, Jimena, Abdel. You guys rocked. Your mentors have said that you kick it out of the park. It means that you rocked it. Congratulations. I know it was not easy, but I can see now that it was worth it, because I was with you every week in your follow-up call. I didn't understand a thing of what you were saying. Now I understand it. So congratulations also about that. I wanna give a shout out again to Link AI, Paula, Diego, thank you so much for working with us in this final project. Thank you to Christian, that he's right here, for the mentorship. And thank you so much to everyone that attended the call and the demo day. Of course, remember to follow the Medium post that Jaime just sent you. And of course, if you have any more questions about the machine learning program, the final project, or anything related to this project, feel free to hit this group on Slack. They will be, I bet that they will be glad to send you. So before, I'm gonna add Abdel here to take a picture about you guys, and I'm also gonna put, so we can remember this amazing day in which you ended Holberton officially. Okay, Abdel, smile everyone. 1, 2, 3. There you go. All right. So thank you so much, everyone.